Hello, my name is Omar Abdelbarri, and I will be presenting on behalf of my group on the polymerization of tetrafluoroethylene to form polytetrafluoroethylene, and our primary focus will be on reactor sizing, reactor type, and optimization of conditions to form the desired product. Let's take a look at what we'll be covering in this screencast. Firstly, we will be looking into our motivation for producing Teflon and why it's such a desired product in the world. We will be defining our problem statement, basically how much Teflon we hope to produce, why we chose that amount, and kind of like a few of the constraints that we're able to set. We'll go ahead and then start talking about our method and approach to achieving that goal. Um, we will then get into the reactor specifics, specifically the design, sizing, and operation of the reactor. We'll be determining how long the operation would take, as that's a key element in producing anything, really. Consumers and marketers would just generally want to know how long it will take to achieve that amount. We'll then be diving into our results and findings, anything important we think that we should be presenting on. Discussion of those results, once again, important takeaways, a couple of bits of advice, a few things that we may or may not do differently, and also our overall conclusion and overall takeaway from this project. Let's take a look at some of the motivations for producing Teflon. Teflon is the primary reagent in making non-stick pans and producing non-stick materials in general for pans, griddles, grills, utensils, and these are very widely used today, and they're a very profitable market also. It's also a good electrical insulator. So for electrical insulation equipment, Teflon is used very wide range in that field. Interestingly enough, it's also used to restrict insect climbing. So if they are objects that you do not wish for insects to be climbing on, you can coat that with Teflon and they will just slide right off because of its low friction. This low friction is even that much low that it almost becomes a non-wetting agent at times. Water will even not be able to bond to it and will slide right off also. So yeah, a lot of good market prospects here for producing Teflon, and it's very widely used. Let's take a look at our problem statement here that we generated, and it was based off of a 2015 statistic that suggested that there was a global demand for Teflon of about 165,000 metric tons. So our group decided to design a batch reactor that could potentially produce about 5% of this global demand. Um, that would work out to about 8,000 metric tons per year. And we break that down even further for a day-to-day process, 21.9 metric tons per day. And so basically, we will be trying to figure out what are the best conditions, the best type of reactor, and the reactor size that would be needed to produce 5% of the world's Teflon. Method that we'll be using to produce Teflon is that of a radical-free polymerization. And here is the net equation for that radical-free polymerization of tetrafluoroethylene, the monomer here. And we'll be using a radical, a sulfate radical. And there are many other radicals that you can use that vary in price and function for producing Teflon and many other useful reagents. Now take a look at our design measurements for the batch reactor. Uh, to achieve that volume of 81 cubic meters, we would need a height of 5 meters and a diameter of the batch reactor to have value of about 2.28 meters, and that heat transfer area right here of about 71.6 squared meters. The idea being that we will charge that monomer tetrafluoroethylene as a reactant 1 and the sulfate radical as reactant 2. The solvent that we'll be using is also going to be water. So basically just fill that reactor up with the reagents and allow that radical-free polymerization to occur. We will be controlling the temperatures and also the initial concentrations of the reactants, which we will see later on that uh, has significant impact on the time and conversion of the reagents. The coolant we'll also be using as water. Here is an equation that describes the time necessary to achieve that 21.9 metric tons per day of Teflon at that given conversion of about zero point 0.9. And basically, we came up with this equation by following the basic algorithm for determining times in batch reactors for reactions like this. I've done that derivation in a separate screencast, so please refer to that if you want to know more about how I came up with this equation and exactly what all these variables are. The main takeaway here, though, however, is that as we increase the concentration of the radical initially, we decrease the time necessary to achieve that conversion, and we note that these tests were all done with holding the temperature of the reagents at about 20 degrees Celsius in MATLAB. And we understand that increasing temperature also will increase the rate of reaction significantly. However, we must be wary of undesired side reactions that can take place at high temperatures rather for the polymerization reaction, and these side reactions could be very dangerous in polymerization and can lead to major explosions and damage of equipment that may end up costing you more in the long run. So it would probably be wise to run such a reaction at a low temperature. One of our major conclusions and major takeaways would be to consider the cost of the radical before deciding what temperature to run the reactor at, as these are the major cost variants for running this reaction, that being the cost of the radical and the energy cost. If radicals are relatively cheap, then maybe it would be best to go with a higher concentration of radicals and a lower temperature. And this would probably be the optimum way to go about this, seeing that it's a lower risk for explosions and health hazards as previously discussed. But we also understand that the sulfate radicals, as they vary in cost depending on the types you have in your location, and the demand for that varies. If you are unable to use much initial concentration of radicals, then you could run it at a higher temperature, but be aware of the increase in energy costs and also the increased risk that comes with this. And you would probably need a lot more safety equipment and to be on your guard, generally a lot more operating at higher temperatures due to those undesired side reactions. Here are some references, and thank you for watching.